Is Herbert. Please.
All right. I want to thank the organizers for inviting me. Sorry about all this technical stuff at the beginning. Right, so I want to talk about almost lowness for k and finite self-information. So first, we should start talking about lowness for k. I think this should be review for pretty much everyone in the room. A real is low for k if it doesn't add any compressive power, right? It compresses about as well as the empty set, maybe up to a constant. A lot of people, right, there's a lot of things we know about this. They behave very nicely. They're closed downwards under Turing reducibility. They're closed under effective join. There are only countably many of them. They're all delta 0, 2. And here's a nice theorem of Nice. Right, being low for k is the same as being k-trivial. So having no compressive power is the same as having no initial segment complexity, right? Being k-trivial, here's the definition, means the initial segment complexity is about as low as possible. We can relax these definitions, right? This is where we get the almost lowness. Essentially, replace the constant with just a slow-growing function, or in general, we replace it with a function. If the function grows too fast, it kind of stops being interesting. So we say A is low for k up to f if, here's the definition of low for k, we throw in the function f of sigma there. And it's k-trivial up to g if we throw in the function g in the definition of k-triviality. So we're going to let this script lk sub f note the class of reals that are low for k up to f, and script kt sub g be the class of reals that are k-trivial up to g. So it shouldn't come as a surprise, right, that the choice of the function is going to affect what the class is you get out. If f is k of sigma, then everything is low for k up to k of sigma, right, because kind of it's not possible. Everything is going to compress at least as good as everything down to 0. If f is just a constant function, you're just going to get low for k out again, right? So we want to restrict ourselves to talking about functions that are going to be interesting. So in particular, functions that are orders. So non-decreasing, really the ordering doesn't matter, but for the sake of concreteness, let's say we're taking the ordering on 2 to the less than omega such that sigma is less than tau if the length of sigma is less than the length of tau. And we want f to be unbounded, right? Because if it's bounded, things get boring again. And almost everything in this talk, we're going to be talking about delta 0, 2 orders. Essentially because there's this result of Bart's and Baum-Paulius that there's a delta 0, 3 order such that you just get low for k back again. So the interesting stuff is going to happen before you get to delta 0, 3. And what's the interesting stuff? Well, in general, you don't get back to low for k, even for really slowly growing f. In fact, for any delta 0, 2 order f, okay, that's weird. You're still closed downward under Turing reducibility. That's great. But you're no longer closed under effective join. In fact, any real is below the join of 2 elements that are low for k up to f. And you're no longer countable. Right now you're uncountable. So you're no longer, all your elements are delta 0, 2. So all the nice things about low for k aren't nice about low for k up to f, no matter how slowly growing your f is, if it's delta 0, 2. And here, right, we had Nice's theorem about lowness for k and k-triviality. In the almost case, it kind of all falls apart in this sense. There's a computable order and a real such that the real is k-trivial for every delta 0, 2g, but it fails to be low for k up to this particular computable order. Right, so not only, I mean, you would expect lowness for k and k-triviality to come apart because now you're talking about up to functions and the domains of the functions are different, so what would it mean for them not to come apart? But here, not only do they come apart in that sense, there's kind of an arithmetical gap, right? It's possible to get the initial segment complexity as delta 0, 2 low as possible without managing to get the compressive power down past some recursive bound. So I'm not going to talk about the proof of that. The main theorems are these things about perfect classes. So here's one for any delta 0 order f. There's a perfect pi 0, 1 class. such that everything in the class is low for k up to f, and for any real, there are two reals in the pi01 class that join above C. And then a slightly stronger thing, there's actually a perfect class that works for every f. It's no longer pi01 because it's a lot more complicated to make the construction work. At the best, I mean, kind of a naive examination gets it to be pi03, but maybe you can do better than that. So there's perfect class Q such that for every delta 0 to order, everything in the class is low for k up to that f, and you still have this thing where you can join above any real you want. So I'm going to sketch the proof of this. The idea is you want to build a computable tree, right, and then your class is going to be passed through the tree. So you need to ensure this lowness for k up to f for every path. So to ensure this, right, you just build a Kraft-Chaitin set. You enumerate descriptions. When it looks like there's a path on the tree that's giving a short description of some sigma, you say, oh, well, I have to put in a description of that sigma that's as good as what the tree is doing, except up to f. So the problem is, right, we're building a tree, so we have a lot of branches, a lot of things, we're going to get a lot of descriptions converging on all the different branches. So potentially, just trying to keep up with descriptions that are converging is going to force us to put too much mass into L. But we have, advantages on our side. We're only trying to meet what's happening on the tree up to f. And we know f is an order, so f is growing, it's unbounded. There's only finitely many things that take any value I. So we can just wait to branch until we're pretty sure that we've seen all the descriptions of things that take value I, and then branch. In particular, we want to branch I plus 1 many times after we've seen everything with value I. I mean, that would be great if we could get it to work. We won't know when that's happened, so we have to kind of try to make it work, and then it will fail, and we'll fix things, right? There's going to be a proof by picture after the proof by words. So if it looks like this isn't working, essentially that means we put the I plus first branching too low, right? And things are converging above it that are descriptions of sigmas with f value I. So that means, well, we just want to push the I plus first branching up. So here's, say, a tree. What we want is on the stem, all the f values of things with descriptions on the stem should be bigger than 0. Then we branch once. Everything on those two paths should be descriptions of things with f value at least 1, right? Then f value at least 2. But then, down here, we have a description converge of some sigma. F of sigma is 1, but it's all the way up here past, the fourth branching point. So that means we branch too early. So we want to move our branching points up. And once we realize that there's this challenge or whatever, we ignore the branch that it came from. Instead of trying to make sure, we meet this, we just find, okay, we need to move this second branching point. So we find the path that the most mass is converged on so far. We keep that one alive. We keep the one alive that looks the same that goes through the other node at the second branching point. We kill all the other nodes, and then we put a branching point as far up in the tree as we got, right? So now we have this bigger area, which is the place where there's only two paths. And everything there, we now have managed to satisfy that all the f values are bigger than 1. We have some new area where all the f values are going to be bigger than 2. The reason we do this we make sure all the branches are identical except for the branching points, right? Because that means there's only, these locations, wherever the branching points end up are the only places where information can be coded in, and that's how we get this kind of non-closure under join, right? Because then if we want to code A in, we just put it in the coding locations. We put A complement in the coding locations of some other path. Those paths will be identical everywhere except for the coding locations, so the join is going to be able to tell exactly what the bits of A are. This is essentially the construction. The there's verification that has to be done, though, right? You have to make sure you didn't spend too much mass. It's kind of clear on the living path that you end up with, or the living tree that you end up with, your mass is going to be finite because, there's some amount of the tree where you potentially paid for mass twice. But if you paid for mass twice, you paid for it with f value at least 1. So you paid half of what the universal machine paid. And then maybe there's mass you paid for 4 times. But if you paid for it 4 times, you paid for it with f value 2, so you paid a quarter. Right? So kind of, if you keep doing that, that adds up to 1, which is fine. There's all the mass that you wasted on branches that you killed because injuries were happening. And the easiest way to deal with that is just to realize, really, you're in charge of the denominators here. So instead of going up by 1 each time, go up by powers of 4. And then if you paid for something twice, you really paid 1/16 what it was worth. If you paid for it 4 times, you paid 1/2 to the 16. And kind of you waste so little mass that it all converges in the end. So the harder case is building a tree that works for all f's. Essentially what you want to do is just exactly that same construction, but keep track of what's happening for all the delta 0-2 orders, and let them all essentially, make injuries when it seems like something's going wrong for them. The problem is you don't know which functions are delta 0-2 orders, right? You just know you have recursive approximations. Some of them are going to be orders. Some of them won't even be total. So you have to just guess which ones are which. Your tree now has branching nodes, and like going for 1 after a guessing node is going to signify that any path through that believes that phi sub e is an order. So it'll be injured when phi sub e says, there's something that converged up here where the value is too low. And otherwise, those paths will just ignore whatever phi sub e is doing. And then there is a series of guesses that's exactly right about which of the phi sub e's are orders. So that series of guesses is going to get a subtree of the tree you construct. Those are orders, so that subtree will actually only be injured finitely often. And by construction, everything, right? By writing exactly the same proof, that subtree, those paths will be low for k for every delta 0-2 order f. So that's that. Now I want to talk about how this relates to mutual information. So here's the definition of mutual information. This is due to Levin. This is probably not the nicest way to write it down, but it's nice for talking about based on the stuff we've already said. So the mutual information, right, it's the log of the sum over all pairs sigma tau of 2 to the k of sigma minus ka of sigma plus k of tau minus kb of tau minus k sigma tau. And the idea is kind of intuitively, if you want to think about it, k of sigma minus k of sigma is like how much A knows about sigma, right? K of sigma, if k of sigma is 10, that means there's 10 bits of information in sigma. If ka of sigma is 7, that means A thinks there's only 7 bits. So the difference must be kind of the bits that A has about sigma that it doesn't need to say, right, in its shortest description. So let's see. Right, if you look at the mutual information of a real with itself, if it's finite, you say it has finite self-information. So here's some easy observations. If A is low for k, then it has finite self-information, right? Because that means in this definition, I can essentially everything in the exponent except the minus k of sigma tau, I can just get rid of with a constant, and then I'm looking at some subset of the domain of the universal machine, right? If A is Martin-Lafrandom, then it has infinite self-information. That's an observation Levin made in the paper where he defined it. And that's essentially right. If it's Martin-Lafrandom, it has a lot of information about the strings that are its initial segments, right? Because those strings have a lot of information, but it thinks they don't have a lot of information. So it must be the thing that has information about them. So here's the proposition, Hirschfeld, Riemann, and Weber. The low for k's are actually, they have this nice definition in terms of mutual information. They're exactly the things that have finite mutual information with everything else. So the proof in the forward direction, kind of the low for k-ness means you ignore the first part of that sum. Then you're just dealing with 2 2 to the k of tau minus kb of tau minus k sigma tau, and you use the symmetry of information to kind of, you replace the k sigma tau with, minus k of tau minus k of sigma given tau, and everything works out. In the reverse direction, if A is not low for k, then it's also not low for Martin-Liff random, right? So there's something that's Martin-Liff random that's not Martin-Liff random relative to it. And that's the thing that it's going to have infinite mutual information with, right? Because B is going to have a lot of information about itself because it's Martin-Liff random, but it can describe itself easily. A is going to have also a lot of information because, right, there's a lot of information in B, but A thinks it's not random, right? So it must be, there must be something that A knows about B to be able to identify it as not random. So I mean, if you use the ample excess lemma of Miller and you, you can kind of work out the sum and everything works out. And this proof is due to Adam Day, but the proposition is due to those three. So we had this that nice result that characterized the low for k's. There was a question whether you could also characterize them as being exactly the things with finite self-information. Hirschfeld and Weber said no. They built a CEA that has finite self-information but is not low for k. But they left open kind of questions about the class of things that have finite self-information, like maybe they're all delta 0, 2. And so this is where things are going to come in from the first part of the talk. The way they showed that there was this thing that was low for k that was not low for k but had finite self-information is they built the delta 0, 2 function such that this particular sum converged, right? And this sum, if you look at our sum describing mutual information, right? We have the sum of sigma taus, 2 to the k of sigma minus ka of sigma, plus k of tau minus kb of tau minus k sigma tau. And so if we can replace this with fhw of sigma and this with fhw of tau, right, which is exactly what we can do if we're low for k up to f of hw, then, right, this theorem says that sum converges, so our sum will converge, and our sum is the mutual information, so it has finite self-information. And it just turns out that f of hw is close enough to be in an order that the theorem we just proved applies, so you can actually just get, this follows immediately, you get a perfect pi 0, 1 class of reals with finite self-information. So they're not all delta 0, 2. There you go. So what does this tell us? Well, it tells us something about finite self-information, right, our definition of mutual information. This is, I guess, a point of contention. This might mean that the definition of mutual information is really bad, right, because now we have a lot of things with finite self-information, but they're not low for k, right, so they have some information in there and they just don't know about it, and maybe that's not something you want in your definition. But maybe you do want it, or maybe you're just okay with it. I've talked to different people. I won't name names, but some people seem really upset, and some people say, no, whatever, it's fine. Right, because maybe it's fine. In general, a set might have information but not know that it has information, right? Because, I mean, how can you tell whether you know about sigma? You have to just look at what the universal machine is doing and look at what the universal machine is doing relative to you. And those will go down, and it might look like you're doing better, but then that drops, and then you say, okay, I'm not doing so well, but then you drop, and you're like, yeah, I'm doing great again. There's no way to tell whether you have information in general, right? But this result also tells us something about these classes LK sub f, right? Because up to now, our results were all just that these classes are really not nice, right? They don't behave like L sub k, or L of k does, right? Just the lows for k. But here we have a class. We know everything in this LK of f has finite self-information. And we know the things with finite self-information behave kind of well. So, right, it doesn't matter, no matter how slow you grow, you're going to have uncountedly many elements, right? And not going to be closed under join. But but it's possible to go slow enough that the elements that you have to add are all relatively nice, right? None of the elements of LK, HW are complete, right? Because they can't compute Martin-Liff randoms. In fact, they're all GL1, right? So you're going slow enough, you're adding uncountably many elements, but you're adding elements that are all relatively low. So it's possible to be nice. Cool. So one other short application, then I'm just going to be done. These are definitions of effective Hausdorff dimension and effective packing dimension. Right, I think, yeah. I mean, one more slide after this. So then a real is going to be, right, low for effective Hausdorff dimension if it doesn't change the effective Hausdorff dimension. It's low for effective packing dimension if it doesn't change the effective packing dimension. And we just have to make this observation that if you're low for k up to a log of length sigma, then you don't change either of these dimensions, right? Because you're dividing by length sigma, so in the limit, log of length sigma over length sigma goes to 0. And log of length sigma is a delta 0 order. So you get a perfect pi 0 1 class of reals that are low for both of these notions of effective dimension. And this was discovered independently by Miller, Ng, Turetsky, and Weber. So I'm kind of on the lookout for other functions where being low for k up to those functions gives you some kind of interesting notion. Let me know if you find any. But that's the end of this talk.
Any questions?
So there was another definition, suggestion of Levin for defining the information for the sum when x is equal to y.
Right.
But how it can it be also used, or what do you think is better definition, or equivalent one, or what?
So as far as I know, it's still open whether they're the same. It's going to have the same problem, essentially having finite self-information is the same as having finite simplified self-information, which is that definition where sigma equals tau. So you're still going to have a perfect pi 0 1 class of things that have finite self-information in that sense. So I don't know. It's nice in that it's easier to work with, and it might be the same, but it might not. I don't know. I've spent some time trying to prove that they're the same, but have not had much success.
Another question? Thank you.
All right, thanks.